je vois et que j'ai le son.
La question, c'est est-ce que quand je parle, on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
La question, c'est est-ce que quand je parle, on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
La question, c'est est-ce que quand je parle, on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
Il y a 30 secondes de retard sur le stream, mais comme c'est le stream, c'est pas.
Voilà.
Ah, parfait.
La question, c'est est-ce que quand je parle, on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
Il y a 30 secondes de retard sur le stream, mais comme c'est le stream, c'est pas.
Voilà.
Ah, parfait.
La question, c'est est-ce que quand je parle, on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
Il y a 30 secondes de retard sur le stream, mais comme c'est le stream, c'est pas.
Voilà.
C'est gentil de partager. C'est comme ça, on peut emporter une partie.
Ah, parfait.
Non mais c'est ma
La question,
méthode.
c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de partager. C'est comme ça, on peut emporter une partie.
Ah, parfait.
Non mais c'est ma
La question,
méthode.
c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de partager. C'est comme ça, on peut emporter une partie.
Ah, parfait.
Non mais c'est ma
La question,
méthode.
c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de partager. C'est comme ça, on peut emporter une partie.
La question, c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de partager. C'est comme ça, on peut emporter une partie.
La question, c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de partager. C'est comme ça, on peut emporter une partie.
La question, c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de ça, on peut emporter une partie.
La question, c'est est-ce que quand
La
je
méthode
parle,
de...
on nous entend moins?
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de ça, on peut emporter une partie.
La question, c'est est-ce que quand
La
je
méthode
parle,
de...
Para caméra, para caméra.
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de ça, on peut emporter une partie.
la question, c'est est-ce que quand
La
je
méthode
parle,
de...
Para caméra, para caméra.
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. C'est gentil de ça, on peut emporter une partie.
la question, c'est est-ce que quand
La
je
méthode
parle,
de...
Para caméra, para caméra.
Oui, oui. Là, le micro, c'est le micro de la salle entière. Donc, peu importe où on est, quasiment, on entend.
J'y ai pas pensé.
J'ai fait là sur le stream, mais comme c'est le stream, c'est pas. Ça, on peut emporter une partie.
la question, c'est est-ce que quand
La
je
méthode
parle,
de...
Para caméra, para caméra.
Oui, oui. Le micro, c'est le micro de la salle entière pour tourner quasiment en entier.
J'y ai pas pensé.
Je vais faire sur le stream, comme c'est le stream. On va porter une
Quand je parle,
Le micro, c'est le micro de la salle entière pour tourner quasiment en entier.
J'y ai pas pensé.
Je vais faire sur le stream, comme c'est le stream. On va porter une
quand je parle,
Le micro, c'est le micro de la salle entière pour tourner quasiment en entier.
J'y ai pas pensé.
je vais faire sur le stream, comme c'est le stream. On va porter une
quand je parle,
Le micro, c'est le micro de la salle entière pour tourner quasiment en entier.
J'y ai pas pensé.
je vais faire sur le stream, comme c'est le stream. On va porter une
quand je parle,
Le micro, c'est le micro de la salle entière pour tourner quasiment en entier.
J'y ai pas pensé.
je vais faire sur le stream, comme c'est le stream. On va porter une
quand je parle,
Le micro, c'est le micro de la salle entière pour tourner quasiment en entier.
Il est connecté là.
Adolfo, did you hear us?
Yes, I do.
Okay, perfect. Can you talk a bit to see if we can?
Yes, hello everybody. Do you hear me? Too loud, maybe? Hi. Testing.
Yes, perfect. Thanks a lot.
Okay.
Everything. You're waiting for Mathieu.
qui donnait son avis sur Iridescent. Tu fais pas partie du jury. Question. On fait un statement. Son mariage. Presque autant l'intro. Alors.
Ok. Tout le monde est prêt?
I'm ready.
So we are here for the defense of the PhD thesis of Gary. The jury is composed by Mathieu Hébert from the Optic Institute and University of Saint-Étienne. Sorry, Doris Gomez from Montpellier and the Centre d'études Centre d'écologie fonctionnelle et évolutive. Adolfo Munoz, that is from the University of Saragosse. The two PhD advisors, Romain Pakanowski and Pascal Barla, and myself, Xavier Granier from Optic Institute also. So you have 45 minutes to present your work, and we are here to listen to you.
So hello everyone, and thank you all for being here for my PhD defense on efficient spectral modeling and rendering of iridescent materials from photonics to computer graphics, supervised by Romain Pakanowski and Pascal Barla. Take a look at this below. Notice how its colors shift and shimmer as the viewing angle changes, ranging from green near normal incidence to purple for grazing angles. This is the phenomenon we call iridescence. It occurs when the hue of a material changes depending on the angle of observation or the angle of the light. More explicitly, iridescence is also called goniochromism, which literally means angle-dependent color. Iridescence is not just fascinating, it's everywhere in nature, creating some of the most stunning visual effects we encounter, from the shimmering shells of beetles to the vibrant wing of some Lepidoptera. We also find it in the body or the wings of other insects, and even in larger animals, like many species of iridescent fishes, or on the feathers of some birds. Iridescent can serve purposes like camouflage, attracting mates, or even warning predators. Beyond animals, iridescence is present in plants, like the Polyaconantata fruit, and in minerals such as opals. While nature has mastered iridescence, humanity has been inspired to replicate and control this phenomenon in many ways. The ability to reproduce and predict the appearance of an iridescent material is crucial across numerous industries. For example, to make iridescent car paint or holographic films on some famous gaming card. It's also used in security printing on currency, passports, and other official documents to prevent falsification or tampering. Reproducing these effects isn't just about mimicking the look, it's also about understanding how to predict the appearance under different lighting and viewing conditions. Indeed, the fabrication and control of various types of iridescent materials remain an active area of research. We can cite recent advancements, such as Liang and colleague work on manufacturing rolls of cellulose photonic laminates, and more recently, Zhang's team developed a method to produce iridescent photonic crystal using inkjet printing. In all the examples we've seen so far, iridescence arises from structural colors. Unlike pigments that absorb and reflect specific wavelengths of light, structural colors emerges from the interaction of light with nanoscale structures. This brings us to a key challenge: how do we bridge the gap between those physical structurations and the visual appearance? For this, we first need to understand the origin of iridescence. There are several materials that may create those type of appearances. Let's begin with thin films. One of the simplest forms of structural coloration, causing the iridescent appearance of soap bubbles or oil slicks. If we take a layer of transparent material with a thickness around few hundreds of nanometers, the light that reflects off both the top and bottom surfaces interfere. Depending on the thickness of the film or the angle of incidence, this interference can amplify certain colors through constructive interference, while cancelling others with destructive interference, creating the vibrant hues we see in the pictures. For a given incidence, if we plot the amount of light that gets reflected by a thin film for all the wavelengths of visible light, we obtain what we call the reflectance spectrum of the material. Here, I've plotted the reflectance spectrum of a 1 micron thin film of glass at normal incidence. Since each visible wavelength is linked to a specific color, from purple to red, the reflectance spectrum may be converted into a single color, which is what would be observed if we illuminate such material using a uniform white light source. We'll see this process in more details later. As you can see, for now, the reflectance of a thin film is rather low, and the shiny color we see in the pictures above are usually observed using a strong light source, like the sun, on a dark background. For illustration purposes, I've increased the lightness of the resulting color by 60% for this slide, next to the actual color. The peak in this plot corresponds to the wavelengths that maximize constructive interference, as opposed to the crest, where all the reflections are cancelled due to destructive interference. The iridescence of structural colors arises from the variation in the reflectance spectrum with the incidence angle. For a thin film in particular, the color shifts toward the shorter wavelengths as the angle of incidence increases. Note that for the bubble or the oil slick shown above, the color variation we see in the pictures are not only due to the variation of the angle, but also to the variation in the thickness of the film. This is especially true for the oil slick. Moving beyond thin films, we encounter another class of materials known as photonic crystals. These structures are characterized by a periodic variation of the refractive index, which can occur in one direction, for example in the shell of certain beetles, two directions with the example of the tubular structuration of the peacock feathers, or three spatial directions as in the crystalline structure of the opal. Like thin films, photonic crystal manipulates light through interference, but in a more complex manner. In such periodic arrangement, the constructive and destructive interference amplified in such a way that for certain range of wavelengths, called photonic band gaps, light is forbidden to propagate through the structure, resulting in a material with a high reflectivity. The resulting color in photonic crystals depend not only on the refractive index contrasts, but also, more critically, on the periodicity of the structure, and is, of course, strongly angular dependent. For a different incidence, the band gap occurs for a different wavelength, yielding iridescence. In my thesis, I focused on two iridescent materials. First, I studied Bragg mirrors, which is another name for a 1D photonic crystal. Bragg mirrors are composed of two thin films of different refractive indices and thicknesses. In the reflectance spectrum of a Bragg mirror, we can see the photonic band gaps mentioned earlier, the position and width of which depend on the parameters of the structures and the angle of incidence. This time, as you can see, the reflectance is strong enough that I did not need to enhance the brightness, right here, to observe the vivid colors resulting from the spectrum. As the angle of incidence increases, the spectrum also shifts towards shorter wavelengths, but the behavior is a bit more complex than that of a thin film. The complexity arises primarily from the variation in the position of the photonic band gaps, which is responsible for the striking iridescence of these materials. The second type of iridescent material I studied is the cholesteric liquid crystal, or CLC. They are responsible, for example, of the blue coloration of the Diplasium crenatoceratum, and cholesteric liquid crystals are also a periodic materials, but unlike the discrete layer of Bragg mirrors, they feature a continuous helical variation of the refractive index. This helix will reflect specific wavelengths determined by the pitch, the distance for one full helical turn. At normal incidence, we can only see one photonic band gaps. But when we vary the angle of incidence, once again, the spectrum shifts toward blue and given rise to vivid iridescence. But we may note that the shape of the band gap at grazing angle is a bit different, with this secondary peak slowly growing. The reflectance spectrum of this structure and also of Bragg mirror is often polarization dependent, another property of light wave that we have to take into account in our models. Before going further on my contribution for those two materials, I'd like to take a few steps back and talk about the previous work that have been made in photonics and computer science toward the understanding and rendering of iridescent materials. Iridescent is mostly a wave optic phenomenon, but in computer graphics, we usually consider light as straight rays following Snell's law of reflection and reflection. To address this limitation, various methods from computational electrodynamics, such as the finite difference time domain, or FDTD, introduced by Kelly in 1966, or finite element methods, have been applied to simulate the wave behavior of light more accurately. There are many papers using this method in the field of photonics. Here I show one example where Yang and colleague used FDTD to simulate the optical property of a modified Bragg mirror. FDTD and similar method allows for the most physically accurate simulations, numerically solving the Maxwell's equations. However, they are often far too computationally expensive to even think about using them to render a macroscopic scene. To solve this problem, more and more research aim at incorporating wave optics directly inside the rendering pipeline. We can briefly mention the work of Ziegler on optical path differencing, where the rays keep track of the phase of the underlying wave. The augmented light field method introduced by O and colleague and the wave BSDF of Creepers and colleagues are both based on the Wigner distribution function. I won't go into details, and are mainly focused on diffraction and simple interferences. More recently, Steinberg and colleagues introduced the physical light transport, bridging the gap towards a more efficient rendering of wave optics phenomenon. Even if all these methods are based on some approximations, they thus reproduce physics phenomena typical of wave optics accurately. They have been used to render large macroscopic scene in reasonable time. However, they still require the separate handling of interference at microscopic level, which is done through the modelization of materials. In my thesis, I choose to encapsulate the wave optics phenomenon inside this material description without changing the way rays are handled. This allows for an easier diffusion of our work within the computer graphics community because our models can be adapted for a vast majority of rendering techniques. For this, our approach is based on the bidirectional reflectance distribution function, or BRDF, which is a mathematical function that takes the incoming and outgoing light directions and computes the ratio of reflected radiance to incident irradiance. In other words, it tells us how much light is reflected in a given direction based on the incident angle. It's a powerful tool that allows for the description of a wide variety of appearance, beginning with diffuse materials, or lumbertion, where the radiance is reflected in all directions evenly. We can also do specular materials, where all the radiance is reflected following the Snell's law toward the so-called specular direction, giving a mirror-like appearance, or glossy materials that reflect light preferentially, but not exclusively toward the specular direction. We can also define a mix of different behaviors to represent, for example, layered materials. Here you have an example of a diffuse base with a smooth coating. Usually, in an RGB renderer, each ray carries the radiance in the form of an RGB vector. In my work, I've also used spectral rendering, where each ray carries the radiance corresponding to one wavelength. For spectral rendering, I specifically used the Malia rendering framework, an open source spectral renderer developed by the Manao team here at INRIA of Bordeaux. MRF generates spectral images where each pixel contains a full spectrum. This has been particularly useful in my project. It is relatively fast for applications, leveraging GPU acceleration techniques to speed up the rendering time. It also features the interactive modification of BRDF parameters, which has been crucial in our research. In order to display an image on the screen, MRF converts the spectral result into RGB at the end of the process. This is done by multiplying the spectrum of each pixel by three functions, X bar, Y bar, and Z bar, known as the CIE sensitivity functions, and related to the biological sensor we have in our eyes to feel the sensation of color. To obtain an RGB vector, we have to compute the integrals of each of these products. In a spectral renderer, this process is done once at the end of the rendering, so the integration can be done numerically. However, if we want to use the spectral definition of our materials in an RGB renderer, we need a way to convert the spectrum efficiently, because it has to be done every time a ray interacts with the material. Actually, most of the previous method used in computer graphics to render iridescence uses the RGB pipeline. We found papers for the rendering of thin film, like the method of Gondek et al., a pioneer on the subject, or the more recent approach of Belcourt and Bala, where they used an efficient Fourier-based spectral integration technique for RGB rendering. Other researchers have explored the appearance of multiple thin films, like the works of Hirayama and colleagues, or the work of Sen. We can also mention some articles about pearlescent materials, such as those of Erstroff and colleagues, or the more recent framework of Guillem and colleagues, using iridescent flakes and matrix transfer methods to render this kind of iridescence. While drag mirrors in CLC has been extensively studied across various fields, we found no prior work in computer graphics dedicated to understanding, predicting, and reproducing their appearances. This gap in the literature is one of the key motivations of our work on these two materials. For this, we've developed a unifying framework for both materials, bridging the gap between photonics and computer graphics. Iridescence is first observed in natural material. At nanoscopy scale, the structures such as the layered interface in Bragg mirror or the helicoidal arrangement in CLCs can be identified. These structures provide key model parameters such as the layer thicknesses, refractive indices, or the helical pitch. Our work begins by using models from wave optics to model how light interacts with these structures, resulting in an accurate spectral reflectance curves that quantify the amount of light reflected at each wavelength. From this point, we have two possible approaches. First, in spectral rendering, we use the spectral reflectance directly within an appearance model, applying a spectral BRGF to generate a fully spectral image. Alternatively, we can opt for RGB rendering, and to make this computation more efficient, we introduce simplified spectral reference model using piecewise constant formulations. These models enable fast and accurate RGB conversion, which is particularly useful for light transport simulation. This workflow provides a unified method that we have applied to both cholesteric liquid crystals and Bragg mirrors. Already briefly introduced what is a Bragg mirror. For reminder, there are 1D photonic crystals made of two thin films with different indices of refraction, N1 and N2, and thicknesses, D1 and D2. The two thin films form a period of thickness lambda, repeated n times. To these structural parameters, we may add theta, the incident angle, that will of course be useful for iridescence. If I plot the reflectance spectrum of a Bragg mirror with a period of 200 nanometers and 5 repetitions at normal incidence, we observe one photonic band gap right here with strong reflectance. Let's see how each parameter influences the reflectance spectrum and its band gap, beginning by increasing n. The reflectance is now even stronger and reaches a value of 1 inside the band gap. Outside, the number of oscillations increased. Now, for the impact of the periodicity, when the thickness of the period increases, it looks like the spectrum is compressed, resulting in more oscillation and thinner band gaps. This also means that multiple band gaps may end up inside the visible spectrum, leading to more complex iridescence. Finally, when we diverge from normal incidence, the spectrum shifts towards short wavelengths, and the two linear polarization behave differently. Up until now, to generate these reflectance spectra, I used PyLama, a stable and versatile Python toolkit for the modeling of multilayered media. I won't go into the details, but PyLama uses transfer matrix method to compute the response of these materials. Due to its validation and robustness, we use this toolkit as a reference in our work. Unfortunately, it has the disadvantage of having a complexity proportional to the number of interfaces, making this solution difficult to use with a large number of repetitions. That's why our approach is based on an analytical formula described by Pochillet, which I would just say it's a simplification of the transfer matrix method that leverages the periodicity of the structure. It yields the same results as the reference given by PyLama, but with no impact on the number of repetitions on the complexity. It's rather slow to fully evaluate on the GPU, but it's not too limiting. However, a problem emerges when dealing with Bragg mirror. It's that the reflectance features oscillation that needs a dense spectral sampling to capture properly. This leads to potential aliasing problem and slow RGB conversion. We want to find a model that is easy to implement, fast to evaluate, avoid oscillations, but also give the same color once converted to RGB. And for this conversion, we need an efficient technique to compute the integral of the product. For this, we begin by using the smooth envelope, although present in Ye's book. This only solves the sampling problem, getting rid of oscillations, but this formulation is not significantly faster to evaluate, and we have no direct way of integrating it properly. Moreover, this envelope overestimates the reflectance, leading to inaccuracy in terms of color. One problem at a time, let's tackle RGB conversion. Since the reflectance saturates in the band gaps, we can begin by approaching them using a piecewise constant approximation, and extend this idea further to the whole spectrum with the height of the boxes determined by the value of the envelope. Boxed functions are interesting because each box can be very easily converted into RGB. For one sensitivity function, here I have chosen the one roughly corresponding to the green, the integral of the product with a box is simply the difference between this area and this area, multiplied, of course, by the height of the box. This can be very quickly evaluated if we pre-compute the cumulative integral of the sensitivity function in a table. Then, the integral of each boxes can be done with only 2 fetches in this table. So much for the integration, but one problem still remains, because by using the envelope, as we see earlier, we kept overestimating the reflectance of our Bragg mirror, especially in these red areas. To end up with a much more accurate color, our final step is to correct the height of the box to take into account the energy lost due to oscillation. For this, we found an empirical angular dependent corrective function that works very well for all combination of Bragg parameters. As you can see now, the color of our approximation nearly perfectly matches the reference. This solution is very efficient, but we miss one key element. To construct this simplified reflectance model, we need to find the position of the bandgap edge to place our boxes. For this, our approach relies on the dispersion relation, which dictates the condition under which a wave of a given wavelength can propagate through the structure at an angle theta. In our case, Ye provides this relation in the form of a cosine function of the wave number, k. On the left, I've plotted this dispersion relation as a function of the angular frequency, omega, which is simply 2 pi over lambda. You'll notice that for certain ranges of omega, the absolute value of the dispersion relation exceeds 1. This indicates that the wave number k is imaginary in those areas, meaning that the wave is evanescent in the mirror. If we compare this to the reflectance spectrum, this region in fact aligns perfectly with the photonic band gaps. Unfortunately, there are no analytical solutions to this equation for locating the edges. So we employ a simple algorithm to find them quickly and accurately. Beginning with what we called the modes, omega m, for which we have an analytical position, and we've proven that they are always located inside the gaps. Then, between 2 modes, we know that the dispersion relation will reach 0 at position we call omega a. We didn't have an analytical solution for this point either, but we can quickly obtain them by dichotomy. Finally, we know that between 2 consecutive omega a and omega m, there will be one edge, which we call omega b, also retrieved using a dichotomy. Finally, we can refine this process using additional subdivision to increase the accuracy of our approximation. All in all, these techniques seem a bit convoluted, but it leads to fairly accurate colors, as you can see on the right, where I've plotted the angular color variation of 3 Bragg mirrors, with the reference spectrum in the middle, a simple approximation on top, and a subdivided approximation on the bottom. We'll see that this allows for rendering scene up to 6 times faster than brute force integration in an RGB renderer, while avoiding spectral sampling issues. When rendering, having a reflectance model is only part of the equation. We also need a BRDF to fully capture the appearance of the material. In natural occurrences, Bragg mirrors are not perfectly smooth. Instead, they exhibit roughness and irregularities at the microscopic level. To account for this, we choose to use a microfacet-based approach, following the classical formulation by Walter Scully. This approach models the surface as a collection of microscopic mirrors, or facets, whose local normals vary randomly around the global normal of the surface. This variation is governed by a distribution of normal orientations, which control the spread of the facet normals to describe a smooth or a rough surface. Additionally, the model includes geometric attenuation, G, which accounts for light being blocked by or shadowed by neighboring facets when reviewed from an angle. Finally, we integrate our reflectance model, either spectral or RGB, into the BRDF formula, and this is equivalent to consider that each microfacet is a Bragg mirror. On the screen, you can see spectral renderings using our WRF Bragg BRDF model for an instance of parameters and different values of roughness. And now I show RGB renderings for another set of Bragg parameters, still with increasing roughness. Here we've compared the reference brute force integration with our simplified approximation, yielding a 6 times speedup. But as you can see, the colors are a bit less intense than the reference, especially for high roughness value. So to improve the accuracy, we used a more subdivided version of the model and still have reduced the rendering time by 3. We didn't stop at modeling a single layer of rough Bragg mirrors, but extended our approach to handle layered structures that incorporate them. In these structures, the light paths can become quite complex, involving multiple transmission and reflection events across the layers. To simplify the problem, we begin by considering only rays that are reflected once by any layer in the structure. Importantly, we observe that the direction of the ray remains unchanged during the transmission through a layer. We call this a ballistic transmission. Leveraging this property, we can efficiently compute the contribution of all microfacets for each transmission event at once. To further optimize this process, we pre-computed an achromatic filter, which depends solely on the roughness and angle of incidence, significantly speeding up our calculation. To validate this model, we compared it to a full Monte Carlo simulation, which stochastically accumulates all possible light paths to generate an image. While our model inevitably loses some energy by ignoring certain paths, it remains fairly accurate. The differences are even smaller when the base layer is absorbent, as less light contributes to the ignorance path. Moreover, our model renders approximately 6 times faster than the full Monte Carlo simulation for the same number of samples, and it requires significantly fewer samples to converge, further improving the efficiency without compromising the accuracy. We've also simulated scatter method measurements and compared the results with real-world data obtained by Schenk and colleagues. For the reflectance, we directly used the thickness and reflective indices parameters provided in their papers. To match the experimental data more closely, we manually adjusted the surface roughness in our model. This process resulted in a qualitatively satisfying correspondence between our simulations and the reflectance measurement. This process has been made easier thanks to our optimizations, which allows the interactive exploration of the appearance of Bragg-based materials. As shown in this video, of a progressive rendering in MRF that quickly converge each time we move a slider to change a parameter, the roughness, the thicknesses, the number of repetition, or the refractive indices. To conclude this section about Bragg mirrors, I'd like to finish on the spectral render that displays a small subset of the appearances our model can reproduce, varying thicknesses, indices, roughness, and the multi-layered structure. Most of the work I've presented so far has been published in a CGF paper and presented at Eurographics 2024. Now that we've explored Bragg mirrors and their optical behavior, let's move on to the second material studied in this work, cholesteric liquid crystals. While both materials share similarities, CLC introduced new challenges. They consist of rod-shaped molecules arranged into a stable helical pattern, with the rod's primary orientation orthogonal to the optical axis, which serves as the central axis of the helix. One important characteristic of CLCs is the pitch, which refers to the distance along the optical axis it takes for the rod to complete one full revolution. The modulation of the refractive index in CLCs is caused by the birefringence of the nanorods, meaning that the refractive index varies depending on how the incident light is polarized. If it's polarized perpendicular to the main direction of the rod, the light experiences the ordinary index, while light polarized parallel to it encounters the extraordinary index NE. From these two indices, we may define the mean index N bar, as well as the anisotropy delta, which are both useful parameters in our modelization. Like Bragg mirrors, we define N as the number of periods in the structure, and additionally, we also consider theta, the angle at which the light wave propagates through the CLC. It's important to note, however, that this propagation angle is not exactly the same as the incident angle due to the way the light bends as it enters into the CLC structure. Similar to Bragg mirrors, I use Pylama to generate reference reflectance spectra for cholesteric liquid crystals. Here, I show once again, on the one I show once again, we can observe the presence of a photonic band gap, but with one key difference, it's that the maximum reflectance only reaches 0.5. This happens because the CLCs reflect light that is circularly polarized with the same indentness as their radical structure, while the other polarization state passes through unaffected. Now let's quickly go through the key properties of the reflectance spectrum and how they are influenced by the material parameters. We'll start with N, the number of repetitions in the structure. As with Bragg mirrors, increasing N increases the reflectance inside the band gap, and also the number of oscillations in the remaining part of the spectrum. When the pitch varies, the position of the photonic band gaps shifts proportionally. At normal incidence, the center of the band gap is located at the wavelength given by the product of the mean refractive index and the pitch. This simple relationship allows us to predict how changes in the pitch directly affect the color. Now, regarding the anisotropy, delta, it primarily affects the width of the photonic band gap. A higher anisotropy leads to a broader band gap. Additionally, increasing delta enhances the reflectance of the structure, making it more efficient at reflecting light within the band gap. Finally, iridescence wouldn't occur without the angular dependence of the reflectance spectrum. And this time, as the angle of incidence increases, the photonic band gaps shift toward shorter wavelengths, and the behavior of the two polarization diverges. As a result, a secondary band gap emerges within the first one, resulting in an overall reflectance reaching a value of 1 for certain wavelengths. Similarly to what we've done for Bragg mirror, we based our work on an analytical formulation of the reflectance spectrum of CLC. However, unlike Bragg mirrors, there is no exact solution to this problem for angle other than normal incidence. To address this, we use the two-wave approximation, a method widely applied in photonics, particularly for studying X-ray diffraction in crystals. Our approach specifically follows the work of Belyakov, whose book summarized the research for understanding the optical behavior of CLC since the 1970s. As you can see on the plots, the two-wave approximation results in green. As you can see on the plots, the two-wave approximation in green matches the reference in red very accurately, with only small differences appearing at large angle of incidence. We observe the same advantages and limitations as with Pochillet for Bragg mirrors, being that the model is physically accurate and its complexity doesn't depend on the number of repetitions, and, however, it's still costly to evaluate, requires dense spectral sampling, and the RGB conversion remains relatively slow. To address these issues, we once again derived a simplified reflectance model And given the shape of the floating band gap, we aim to approximate it using a piecewise constant approach. Similar to what we did earlier. When a secondary band gap appears at larger angle of incidence, we extend the approximation by adding multiple boxes to account for this new feature. This time, however, we found a way to analytically determine the band gap edges. For this, we also rely on Belyakov's work. Specifically, to compute the two-wave approximation, we use a reparametrization of the wavelengths that depends on both the material parameters and the angle of incidence. When we plot the reflectance spectra in this space, something interesting happens. The band gaps all appear around delta equals 0. In fact, by observing the dispersion relation of CLCs in this new space, we can analytically determine the edges of the band gaps by solving polynomial equations. This is what is summarized in this complex looking diagram. Let's quickly break it down. At normal incidence, on the bottom, we divide the band gaps into two ports from delta equal -1 to 0 and from delta equal 0 to 1. As we increase the angle of incidence, the secondary band gaps appears, which is represented by the purple area in this diagram. In this region, light is reflected regardless of the polarization. Further increasing the angle of incidence, we observe that the three regions start to separate and holes appear where the reflectance drops significantly. To complete the modeling of the band gaps, we also need to determine the reflectance of them or the height of the boxes. For the red and blue areas, we have an analytical formula that depends on the CLC parameters. However, for the purple and gray areas, we used pre-computed tables because we couldn't find an explicit formula for these regions. And for the remaining part of the spectrum, outside of the band gaps, we developed an asymmetrical smooth approximation. It behaves roughly like a 1/delta squared, and it captures the decaying part of the reflectance outside of the band gap, without the oscillations. To convert the simplified model into RGB efficiently, we use the boxes in the same way we did for Bragg mirrors, and we also found a way to efficiently integrate the decaying part of the spectrum without using boxes. For each side, we just pre-computed 2D lookup tables from which we fetch values based on the physical parameters to compute the result of the integration. This gradient I show you demonstrates that our model accurately reproduces the color compared to the reference represented by each middle row. And that our fast RGB integration does not introduce any additional errors. We can also observe how color changes differently depending on the physical parameters. We have incorporated this model into a PRGF, similar to what we did for Bragg mirrors. However, instead of reproducing a rough surface with a distribution of macrofacet normals following Walter's formulation as shown on the right, we modeled a smooth surface with a distribution of orientation of cholesteric domains, as shown on the left. The equations are a bit different, but both models give close results, with the variation only becoming noticeable for high roughness, as seen on the bottom picture. The final aspect we've incorporated into our model is the pitch tilt coupling. During the fabrication process of some CLC materials, a solution containing nanorods solidifies into a gel-like film, and as it dries, it forms cholesteric domains. If the drying process continues, two things will happen. First, the domain will gradually realign towards the surface normal, changing the finite orientation distribution. And secondly, as the structure compresses, the domain which were initially aligned with the normal experiences more compression, leading to a variation in pitch that depends on the tilt direction of the domain and the compression ratio alpha. Qualitatively, this results in iridescent halos around a highlight, with the color controlled by the initial pitch we give to the cholesteric domains before drying it and compressing it. We compare our BRDF model to optical measurement from the work of and colleagues. These measures show the amount of light detected by by a sensor after a reflection on a cholesteric material. This is a function of the wavelength and the sensor orientation for a light source placed around 15 degrees. Our model, on the right, shows a good accordance to these measures. However, it's important to note that we don't achieve a perfect fit, notably for the specular reflection, and it's likely due to the incomplete modeling of the air-film interface. Our model also allows for spatial variation of the parameters. In this example, we've used a noise texture to modify the pitch around a mean value, and the baseline is shown on the bottom row. If we vary the pitch, the color vary accordingly, and you can see on the upper picture that we have a kind of a noisy color pattern. To conclude on CLCs, I want to show the spectral rendering of a microscopic scene with several objects exploring the possible appearances of CLCs. With, for example, the sphere on the middle, or without the pitch tilt coupling. Overall, the expressiveness of CLC is less diverse than those of Bragg mirrors, primarily because they feature only one band gaps, whereas Bragg mirrors had multiples. To conclude, I have presented a uniform framework for efficiently modeling and reproducing the appearance of iridescent materials, specifically Bragg mirror and cholesteric liquid crystals. In this work, we've introduced concepts from photonics and research from the field of electromagnetics into the computer graphics community. This includes key contributions, such as the reflectance formula developed by Pochillier and Vladimir Belyakov, which allows us to model the reflectance based on the physical properties of the structures. To address the need for efficiency, we developed simplified spectral models with the goal of reproducing the same colors as the physically accurate result, but in a form that enables fast computation within an RGB rendering pipeline. Additionally, for both materials, we've introduced several BRDF models inspired by prior work in computer graphics, tailored to capture the unique behavior of Bragg mirrors and CLCs. Even so, we've already discussed a lot of things regarding iridescence in my 3 years of PhD. There are still a lot of things we can do to improve our framework in the future. First, one of our major limitations is that we only considered irregularities at a microscopic level, using the BRDF and considering only perfect structure for spectral models. However, in natural materials, we often have nanoscopic irregularities, and further work may aim at taking these irregularities into account to quantify their impact on the spectra and the scattering of light inside a new BRDF model. Finally, we can imagine that using our simplified model, we can ease the process for inverse design, retrieving the physical parameters from a desired appearance. In other words, going from computer graphics back to photonics. And I would like to thank you all for listening to me.
Merci. Thanks a lot. So, taking a bit of breath, we can start to have some question by the member of the jury. And the tradition is that the person that is coming from the further distance is starting. So I think Adolfo, if you can ask the first question, welcome.
Okay. So hello everybody. Before asking the first questions, I want to congratulate Gary because this has been a very Gary and supervisors. Okay, because there is a shared thing there. But yeah, this has been a very, very amazing work. I have loved every part of it. I am very interested in how wave optics affect appearance, and this has been like a novel take on it that I have learned a lot from. So congratulations on that matter. Okay. And I have I have a million questions, but I will summarize in the most interesting ones for me. Okay, so my first question is about the BRDF models. In both cases, when you have like the reflectance spectrum, you can use that reflectance spectrum as part of. You need to use that reflectance spectrum as part of a BRDF model, okay, in order to render everything. So in Bragg mirrors, you use an approach that is common that also was used by Belcourt et al. At the moment, which is you use a microfacet model and replace the Fresnel reflectance with your particular model. However, in the case of CLCs, you haven't done exactly that. Why the difference? I am asking out of curiosity because I thought you were going to do exactly the same thing until you didn't.
Yeah. So at first, we started by using the exact same model. Let me just go back to this slide. Right here. So at first, we begin by using the exact same model, the microfacet BRDF. But we found that the actual structure we wanted to reproduce is not made like a rough surface. You know, it's more like a smooth film, and under this film there are these rod shaped molecules that have the optical axis of the helix that will be orientated with a certain distribution. And so you don't have geometrical peaks and crests that may, for example, cast a shadow on the remaining of the neighboring microfacets. So that's why in this equation you don't have the geometric term, for example. You don't have the geometric term because there is no shadowing of the cholesterics domain 1 and 2 the other. And after we've done some calculation to ensure that that this model is physically accurate, meaning that we want to create or lose energy more than that. We will lose energy because of the projection, but we don't create energy, and that's what imports us the most. So yes, it's just to account for this specific structure of CLCs, which are a bit different from the other structure made with Bragg mirrors. I don't know if I answered your question.
Yes, it's very clear. Thank you. My next question is about light polarization. Okay. You have shown that there is a significant change on reflectance in CLCs particularly, depending on the type of the polarization of the incident illumination. Okay.
Yes.
So the thing is that I understand that, of course, once you start doing all these approximations, you are approximating the unpolarized light, isn't it? So I would like you to speculate what if instead of creating BRDF models, we were proposing creating polarized BRDF models, models that account for the polarization state. So how would your methodology change on that regard?
So the main change that will occur for taking polarization into account in the case of CLCs is that, as you can see on this plot, the shape of the polarized reflectance are not really as box-like than the unpolarized reflectance model. However, if we want, we can still use all the process I've introduced because the dispersion relation we used to retrieve the edges of each of these polarization band gaps the dispersion relations are computed independently for the two polarizations. And so we have the edges for the first, we have the edges corresponding to one polarization or the other. So we can use the same techniques with different arrangement of boxes based on the edges we've computed in our framework. And for the spectral rendering part, the formulation we have is already polarization dependent, so we can still, for the spectral rendering part, we can evaluate it with the full formulation. And yes, for the RGB renderer, by using still a piecewise constant approximation, I think that we could retrieve a very accurate model even with polarized BRGF.
Do you think that you would you would have the same box boundaries, like in the same structure for both polarization states, or yeah?
Yes and no. Sorry, we will have the same edges.
Yeah, exactly.
Predicted by this picture, by this diagram, but the repartition of the band gaps belonging to one polarization or the other is to evaluate, because when you see when you look at the spectrum, when you look at the difference between the polarized spectrum, once again I will go back. You can see that the edges of the red or the blue curve are still aligned with those of the green curve. So we can use the same edges as we do now, but we have to distribute the boxes between each polarization according to a new model that computes the height of those boxes.
Okay, so thank you very much. Yeah, makes a lot of sense. And my last question so far is it's something about something that you have written in the document, which seems to be very interesting. Which is how do you invert these models, right? So ideally, so you have shown some agreement with measurements in the case of Bragg mirrors, if I recall correctly. Okay, so ideally, what would you, and you have shown some in the document, you have shown something about the inverse problem of this model. So would you please develop a little bit of how would you invert these models to match some measurements or some, I would say photographs, but that would be much more challenging, some measurements?
Yes. Well, I don't have really research on this subject, but we have always wanted to aim toward this particular problem of inverse design, and for this we may, I don't really have a method, but we may use the simplified model, which uses these simple boxes and are determined by the parameters, and we can, since the integration of the I will take a step back. So I think it will be easier for CLC. Why? Because since we have only one band gaps, or one divided band gaps, but globally you can still fairly well approximate the color with one band gap, and the color of one box can be fairly easily induced using the position of the box. the inverse problem might be more or less difficult because you have fewer parameters. If we don't take polarization into account and we don't use the 3-box model, but just 1 box, there are only 3 parameters: the left edge of the box, the right edge of the box, and the height of the box. And with this just 3 parameters, I think it's very easy to have a full palette of reachable colors varying this only 3 parameters. It's maybe a bit chaotic in how I say it, but with only 3 parameters and a 3D space of colors, since we can, if we pick a color in this 3D space, we have the edge of the box and the height of the box, and since we have analytical solution, we just need to inverse our functions, or 1D function, 3 1D functions to retrieve well, the parameters of the characteristics. Of course, there will be multiple. Sorry, yeah. An infinite. Sorry. Yes. There will be an infinite parameters of characteristics because we have more than 3 parameters for describing them, but we need ideally only 3 parameters to find I lost the word. But to find an equivalent space.
And how often do you think you would have multiple solutions for the same exact appearance? You know what I mean?
Yes.
So is that very common, or that should happen very few times?
No, I think it would happen a lot of time actually, because the converting the spectrum into a color, you have typically a metamerism. So you will have so, well, I would say maybe not exactly, but
Yeah. Yeah, I get it. So yeah, so the metabolism is going to happen like
I think it will going to happen, but actually I haven't done it, so maybe
yeah, okay, yeah, somebody else's problem at some point, yes. Okay.
Yes.
And I promise that this was the last, but the really last one, okay. I am very curious. So you have shown how approximating the spectral reflectance with piecewise with boxes, basically with piecewise constant functions. Okay, works very well for speed ups, and it's reasonably accurate. And in your document, you compare it with piecewise linear. Okay, saying that in the end it's more worth it to just remain on piecewise constant, particularly for Bragg mirrors. Have you considered? So it is kind of surprise. So I understand that the how easy is to integrate everything with piecewise constant. Okay. I was thinking that due to the many oscillations on both reflectance profiles, maybe other types of functions like frequency, whatever basis, would work better. Have you considered? Have you tried or have you considered other projecting into other basis functions besides piecewise constant?
Well, not really, but at the beginning of the project on Bragg mirrors, of course, we were based. We based our approach on what have already been done, notably in the model of Belcourt and Barra. And in their method, they use a Fourier-based approximation for the oscillation of the thin film reflectance. But in Bragg mirrors, when you do a Fourier analysis of the spectrum, because of the band gaps, it's really hard to obtain something interesting. maybe there is a solution by tweaking the spectrum before the analysis for excluding the band gaps once we have found them, but we've not explored this path for now.
Okay. So yeah, so thank you very much for all of your answers. Again, I want to congratulate you and your supervisors, okay, for this job, which has been a pleasure to read, very easy to follow, and I have learned a lot. And I will leave the floor for other jury members. Again, congratulations.
Thank you very much.
Thanks a lot for this question and for the report. And I think the question are coming from Mathieu.
Thank you, Mr. President. No, keep quiet. Sorry for disturbing just before. It's just, I have no answer anyway, so I won't tell you that what you are saying is wrong. Just interesting. I'm a bit more optimistic than you seem to be. So we will discuss that after. Okay. No, first of all, I would like to really congratulate that report. Was very very interesting in the topic, very well written, and it was a pleasure to read it. And especially when I am not an expert in computer graphics and not an expert in this kind of interferential structure. So I was not an expert in both domains, but I could follow everything, and it was clear. So, and it is mainly because you wrote it in a way that is really accessible. So, congratulations for that. Also, I said in my report, it is really striking that you could do physics and computer graphics, and it is not so easy to relate the two. So it was very, very interesting for that. I could also observe in your presentation things that we could not do in the report, all the animations where we see how it varies. It was wonderful. Before entering into other questions, most of my question will be maybe in the unthought of that work, so the ground. But before that, what was your education before starting your PhD?
I did I was at Institute of TIC.
I did not expect that answer. So
yeah, so I did.
Forgot maybe your lessons in radiometry.
I know what you're talking about.
No. Did I send to you my?
Yes.
Okay.
Yes.
Just to be sure. Yeah.
Thank you.
No, I speak of radiometry because maybe it is the domain I know better, but also when we want to relate physics to something that is displayed through a sensor or the eye, the link between the two is radiometry. And so that's why it is always interesting to look at this rigorously, because it is a pity to do so beautiful physics, then and in the end we have pixels, but in between, okay? And for example, my question was, maybe you was from computer science, and in computer science we say reflectance spectrum. I know that. I learned photometry through computer science, and it is said reflectance spectrum. In radiometry, we did spectral reflectance. And besides that, well, it is just word, okay, not just that. A spectrum is well, a distribution of a signal. Reflectance is not a signal, it is a phenomenon. Well, the quantity related to a phenomenon. So to say reflectance spectrum.
Yeah, no, see.
With that, okay. So spectral reflectance. That is anecdotic, but I will recommend to no, forget that. I have this because I will switch to something similar about the BRDF. Once again, BRDF, there is a mathematical representation of BRDF and a physical one. And you are just in between, or you are switching from the one to the other one. So how many parameters, when we say BRDF, how many parameters?
Yes. Well, in computer graphics, usually we consider 4 parameters. 2 parameters. The incoming direction and the outgoing direction.
Okay.
In reality, you have more than that. You have first the position at which you evaluate the BRDF on the surface. So that's already 3 or 2 surface dimension just for the coordinate of the surface. In computer graphics, this is what we call the spatial varying BRDF. So a BRDF in computer graphics is one function applied to a complete object regardless on the position. And then in computer graphics, once again, each direction is just one vector, but it's in physics it's 3-dimensional vectors. It's a 3-dimensional vector. So in physics it would be 6 dimensions, but in a computer it's only 2 vectors, so 2 dimensions. Maybe
I think 11.
Yes,
Are missing.
because I told about this.
No, you're right. Position,
6 positions,
wavelength,
and the
reflectance, polarization, polarized reflectance. What else?
Yes, polarization.
And that is something that is not necessary in computer science, but
Yes,
solid angle area.
yes. It is actually, it is really important even in computer science.
Yeah, because if you go from electromagnetism
Yes.
to what will fall in,
We always need to account for the
and there are many questions on that, because if you have so a vector, so in optics a plane wave that you eliminate a rough surface or a structure like that, what do you obtain? You have a monochromatic plane wave, rough surface. What do you obtain?
you have a
If you are from Massive to the Peak, you know. I know that you know.
3 years ago.
Actually, you have speckle.
Yes, you have speckle. Yes.
Yes. In physics, you have speckle, and probably that's why the electromagnetic codes cannot be extended to large surfaces. Is that you have the speckle related to a small tile, and if you have the same surface but another place, you have another speckle, and it is only the average of all of that that gives the BRDF. And I just take time to insist on that, because between electromagnetism, radiometry, and what we need to color the pixels in an image in computer science, there are steps which are important. Okay, so BRDF is a speckle where the granularity is so thin that we smoothen and we don't realize that it exists. But in your case, as you look at electromagnetism, I have that in mind. I stop with that just to replace radiometry in a place. Now we switch to colorimetry. I don't understand. It is another problem, colorimetry. You have physics, so spectral reflectance or spectral signal, and you want to feel RGB values in an image. Why do you need XYZ? I didn't understand why we need to consider the 3 stimulus values XYZ.
Maybe I didn't. maybe that's something I missed, but
It is on the slide 28.
yes, but I don't understand why how
Actually, it is so maybe an unthought. I see that everywhere. Yeah.
Here I did not show the whole process to convert the spectrum into an RGB mode. Yes, I have the
No,
X-Y.
but I had the same question in the report actually.
So why would I? Sorry. For me to convert a color is just something we humans see and called color, but to from a random spectrum, you don't have any color associated to it without something or someone to see it through a sensor.
That's a big question. Actually, XYZ are not the response of a signal at all. I discovered recently that in the manufacturers of camera, they try to have filters that reproduce these functions. It is silly. It has absolutely no sense. It is just an RGB, the RGB space from there. It is mixing of colors. So it is the result of mixing laws and metamerism in mixing laws. Nothing with electrical response or visual response to signal. Okay, and XYZ is a mathematical transform from these mixings. Okay, so it is very good in naming or labeling colors, but it has nothing to do with sensors. And yeah, I know that nobody knows. and so why not directly taking, I don't know, the spectral response of a camera, of a standard camera, of I don't know, and it would gain a step actually. Okay, so just what you are not aware.
Frankly, I was not aware, okay. but it's really interesting, and I did that because usually in the field of computer graphics, when we want to convert a spectrum to an RGB color for human perception, we use those XYZ function in the literature.
Yeah, I know. I know that everybody does that. Everybody.
Maybe we should do to
something that clearly we need to question. Well, it is easy to do that. Okay, color is complicated, and I think it is for facility. But as far as I can see, for at least 60 years, we do not question practice, and especially for iridescent color. I have worked a little with plasmonic color with some iridescence. What we could observe is that when you have a real object, you have beautiful colors, strong colors, as you say in the report. When you measure them in a color space, the color gamut is very small. Small. In our case, it was very small. But the brain is much more clever than the experiment that have been done. You know, XYZ RGB has been done in the black with something that is at the center of the view, not complex object as an insect in the forest, right? And the brain understands that there is iridescence, and it increases the gamut. Okay, so the iridescent color is always more colorful than what could be measured physically. So, once again, why necessarily using that for being representative of the human vision, as we know that it is not representative of human vision? So it is one more argument that go directly from your spectrum to the sensor and to be faster.
And actually, the method won't be any different with another sensor.
For sure, you just gain what you do the same, but with sensor, and you gain one step. Yeah. Okay, now a question on the physical part. So you speak of a matrix in a Pilana software, right? You say that it is a matrix matrix model. Yes, it is Abel's matrices or something like that. It's similar to the theory of thin
Yes,
films.
it's quite similar to Abel matrices
Anyway,
or RBCD model.
yeah. So for the
Yes, it's just
magnitude of the electrical field.
exactly, and you have each interface. You have a diopter.
Yeah. Okay.
Diopter
I see.
matrix and a propagation matrix for each medium. And actually, in Pylama, there are two different methods, matrix method, the transferred matrix method, yes, and the scattering matrix method, which propagates in both ways the signal. It's for numerical stability.
Okay, so more complex than simply thin films, but okay, I see why it is so accurate. And you know that there is the equivalent for not electromagnetic field, but for flux. So when you have no interferences, and I think that in the case where there is a background, I saw that you stop by saying that there is a transmission, reflection and transmission, and something is missing for the multiple reflection, you said that. And I thought that actually it is rather easy to add with the flux transformacy, provided that, so the light enters, it is scattered by the background and just say it is Lambertian for facility. It means that you integrate the angular reflectance of your Bragg mirror over the hemisphere. Do you know the reflectance at all angles? The reflectance, yes, at all angles, you know it, yeah. Would it be long to integrate over all the angles? That was my question. Maybe why you didn't do that?
We have talked a lot with Pascal, notably, about this, about what we would call the reflectance filter. You know, for our simulation, here we had computed a transmissive, a filter for transmission.
Yeah.
Because the direction is not changed by the transmission. But for reflection, we already had in mind what happened when we come from the top, from a given direction, and we want to integrate all we want to integrate the reflectance in all direction. It's to have like a directional albedo of the whole structure, and we have still problem about this. But from below the surface, once you've reached the base, maybe it's easier because of this even distribution we have, and we did not try it, of course, but yeah, I think it would be mathematically feasible, and maybe even have, like we did, some kind of pre-computed filter that does not depend on the Bragg parameter at all, and just recompute the Bragg accepted roughness, and just recompute the spectrum using the parameters and the spectrum, and this would actually separate the dimensions of the.
Can you show the rainbows that you obtained in your simulations? You know that there is a kind of rainbows as a function of the angle. Where is it? On the flat samples? Yes. On the abscissa, it is the angle. Yeah.
Yes.
Okay. So it means that you need to integrate that, so the spectral quantity that is below, to integrate that times sine 2 theta. Okay. And you have the bi-hemispherical reflectance, so just the quantity that you need, and you have an analytical formula, and that's it. And you have everything. Because, you know, after your Bragg system, you enter into a Lambertian material, your light is depolarized, you have no memory of the direction, no memory of the polarization, you just reset. So you re-illuminate with incoherent diffuse light, and you can use just a formula for multiple reflection between two components, provided that you have the bi-hemispherical reflectance, so the integration of that. But I was saying, maybe it is not colored, that component. Yellow and blue, they are opposite. That would be interesting to see if you do the summation, the integral. Is there a strong dependence on wavelength? So is it colored?
On wavelengths, yes, because you can
integrate.
Yes, because with some parameters you can have like only yellow for the whole spectrum. With here you see you don't have all the wavelengths for a given Bragg-Myers. So yes, for the wavelengths.
So you mean that you could have a kind of rainbow like that where you have only yellow?
Yes. Yes. Okay. If you take if you place the band gaps where it should, maybe not for yellow, but you can have one.
So at least in that case, if it is colored, let's say you need to take that into account. Otherwise, in situations like below,
maybe
if it is achromatic,
maybe it's like
that way it is just a small formula, and I think you can have something accurate without any time computation. That's my feeling. But we can discuss that below.
It's really interesting.
The formula is very easy. And on slide 56, I am out of the computer graphics community, and when I see that the 56, yes, the time computation is divided by 6, my first feeling is that, well, that's good. But I have also in mind, I saw some examples where 1 day of computation is decreased to 2 minutes. So more the 1 order of magnitude or 1 or 2 order of magnitude. Here it is only by 6.
It's only 6 for the same number of samples. And it's what's really important for this particular model. It's that I don't know if you see really well on the projector, but actually for these two spheres in a very simple scene, I use 30,000 samples by pixel. So each pixel I send 30,000 rays, and you see that even with this much samples, you still have like some noise on the simulation, whereas the model is perfectly smooth, no noise at all. And in it, we maybe need 10,000 times less samples to render the same scene with the same amount of noise. And it's there that the benefits or what it lies. Moreover, well, I won't develop much more, but with a Monte Carlo simulation, you don't know when you enter the material where you're going to go out of the material.
Yeah. And I had that.
It causes a lot of problem when you want to sample both the light source and the camera.
For sure. On the next slide, I wrote it. Congrats. Yes, I love that. So, but yeah, for sure. Of course, there are some differences, and I'm not expert enough to say what to see where the differences are. So, but I know little. I have seen things on these electromagnetic structures, that's nanostructures, how it is hard to predict the colors. And when I see that, well, I really say congrats. Yeah, and the similarities, very impressive. And from that, I finish with my last question. I have even still 1 minute for the last question. Yeah. It is again for the inverse approach. Of course, we're interested in that. Oh, we could start with the image with the insect. My question was, well, you have the picture of the insect.
Which one?
This one.
Yes.
It is a picture?
Yes, it's an actual photograph.
It is a photography, yeah, good. From the photograph, assuming that the structure, the microstructure is the same on the whole insect, which is maybe not the case, but say, from that picture, can you retrieve the microstructure? Or the parameters, I don't know,
To some extent, for now, by ends, more or less, because at normal incidence, we can, if we take like small periods for the Bragg, with small period, as we've seen, there is only one band gap in the visible spectrum, and we can predict the position of the band gap very accurately using the Bragg condition. Because this band gap, one of these band gaps will be located at the product of the index and the period. So, for example, if I wanted to have, I don't know if it will be the same iridescent, but at least at normal incidence, if I want something that will be green, for example, I can say yes. So green is 600 nanometers, give or take, and if I know that this type of materials usually have refractive index around 1.4, 1.4, 1.3. Well, you just divide 600 by the index, and so you can kind of predict the period you need for the Bragg. From that, it's more complex. If you want to have the same angular variation as your reference, especially within only one.
But you can see it on the picture. You have many angles on that.
Oh yes, but it's
so that's why I wanted to say that I am more optimistic. Actually, you don't have only one pixel. You have a lot.
Yes. To retrieve the angle from just the photograph, to retrieve the angle of the normal from just the photograph, at least we need a mesh model.
Okay, assume you have the mesh. I agree. It would be too much. I agree. So assume you have the mesh plus the picture, and yeah, I'll give you an example that is actually similar. You know, when you have something like that,
yes,
it is not flat. Here you see a color. If it is homogeneously illuminated, here, because of the interreflections, you have a gradient. If you take an RGB picture of the gradient, you can retrieve the spectral reflectance as good as if you measure it with a spectrophotometer. Almost. Because the gradient is not proportional to the reflectance, but it is nonlinear. So you have one information per pixel. One color and one information. If you have as many pixels as you need parameters, yeah, you can retrieve it. And that's very surprising. That's not intuitive, I know, but it works. So here, if you have the shape, you have many angles, and you have a rainbow,
yeah, but
you have a lot of information.
Homogeneous, the same structure everywhere, which is not in biology.
Okay, sure.
Sorry.
No, that's why that's
yeah, but
there will be some pixels. Yes, there will be some.
I ask with the insects. I'm sure that it is the most difficult. Maybe from an image that you have simulated, you forgot your simulation, you take it and you go back. Can you retrieve some information?
Yes, but even if you can ideally retrieve the spectrum or material with this method, it's not sure that we can retrieve the parameters of the structure from this spectrum.
So
it's more this path that I'm more pessimistic about.
Depends depending on your observation. Did you observe two very different structures that display the same rainbow? The same rainbow?
No, the same rainbow.
The same color at the same angle, of course.
But the same rainbow, I mean,
Take 10 angles, 10 different angles, and you have exactly the same colors with two structures. Is it frequent?
I don't look for them, so I don't really know the answer. But my intuition is that with this I mean, for just a smooth Bragg mirrors, you have like 6 parameters. Well, no, 4 parameters, plus the angle. And in this, I don't know actually the full the full dimension of those gradients. No, but my intuition is that the dimensionality of the gradients is lower than the dimensionality of the structure. I don't have any proof for that. So
That's the question.
I want to say I don't know.
I would say yes, personally, intuitively, but your intuition is okay. Okay. So let's keep that question open for next. But I remain a little more optimistic than you. I think that once you are able to predict the rainbows, say like that, I think that the inverse problem is not so maybe easier than you think.
I really don't know, but I would so much like to find this.
So let's wait the next PhD on that topic to have the answer. So thank you. Sorry for all this time, but again, really congratulations.
So I propose it's your turn to ask some questions.
Okay, well, thank you very much, Gary. So, okay, I have multiple congratulations to give you. First, to have chosen me, because I have nothing to do either with optics or computer graphics, so good thinking. And then it may seem strange because I was a bit lost in equations in your thesis, but I really liked it. Despite my poor understanding, I was really like taken by the flood floor, and it was really you really put a large effort in making it pedagogical and with beautiful figures, well explained in the legend, which is really good for me. And they came at a point when I really needed them, so that was really good. And with LaTeX and colors and so on, it's really nicely written, and it all reads perfectly. So at some point I would need, but because I'm not a specialist, a general glossary, because I was a bit lost in acronyms, but that's okay. And because I'm a biologist, I will make a point. Species names are not well written because you're not a biologist, so we are a bit rigid on that. So names have to be in italics with a major capital case for the genus and not for the species, and so on. So I was like, okay, well, I have only one small comment to make. I'm relieved. There's something not so perfect. But apart from that, that was really good. And I congratulate you too for your presentation, because I suddenly discovered a new thing that I hadn't seen in the report. I completely understood the story differently, so that was good. And so I will ask a few questions. They may sound weird, maybe, or completely out of focus, but that's the thing of inviting a biologist. You have to be ready to awkward questions. So the first is about this inverse problem, because I was like, that's really cool. And we all also dream of it in biology, of from the spectrum, guessing the pigment, from the spectrum, guessing the structure. And I was slightly optimistic, not from the homogeneity of the biological structures, because from experience they are not. But I was wondering, given that in nature materials have a small range of refractive indexes, a small range of bricks that they can build on, maybe it restricts the space of possible things. And maybe because evolution always plays on some aspects and not others, because it's not possible in nature, maybe because of that, you could guess a space of possible that would be more restricted and more interesting to dig in.
Yes.
From what you can have, like pictures or.
So, actually, yes, and it's really good. I am already on this slide, because what this slide shows on top of the good accordance of our model is that modeling the microscopic irregularities with only a very, I would say, a very coarse microfacet model, already you can have the same like gradients and the same mixing of colors as we observe on the pictures and on the measurement. And this is something that we found and that we want to explore a bit more to see if we didn't miss anything in the nanoscopic irregularities. That's why I talked about it in the perspectives. But yes, just our microfacet model already encapsulates the variety of the structure and the irregularities fairly well. So this is the first step. So our model can be used to retrieve the appearance pretty well. And from this, of course, yes, the space can be divided and we can erase a lot of portion of the space of the possibility, because you cannot have a beetle elytra with an index of 2.4. You cannot have a periodicity of I don't know, 2 microns, or I don't know the answer, but you know, so of course you are limited in the parameters, and that could vastly ease the process of inverse design. And yes, if we want to follow in this direction, it's the first thing we need to do is to reduce the dimensionality. And for natural materials, yes, it's taking into account evolutional limitation we found in nature, such as the indices mainly, but yes, in the thicknesses. Also, the ratio of thicknesses found in nature cannot exceed some. You cannot have one person one material and 99% of the other, because you're you're limited. Sorry.
And in these dual beetles, like the general family, well, they have a curvated elytra, and they also have, when you had put some photographs zoomed, you can see holes. And what kind of optical effects do you think it has, and could it improve your modeling if you took it into account? How could you take that into account, these holes and the whole shape? Do you already take that into account, or?
No, I did not take that into account. Actually, these holes they are just a bit too big. They are just a bit too big for our representation. Our model will try to reproduce around the color around the holes. What I think would be the more adapted approach would be to model this these dark spots in a spatial variation on a model. So just have a different type of BRDF for these holes because they are not Bragg mirrors. You don't have to use a reflectance model. But if you want to have like, the general appearance when you don't actually see the holes because you're too far away, you know, in this picture you can still see them. That's why I say they are too big because you would need to spatially define them. But if you want to have the mix of those two appearances, when you look at it from further, maybe you can do like some stochastic approach where with some percentage of the time you use our model, with another percentage of the time you use just an absorbent material, and overall you will reduce the brightness of the insect.
And in general, I'm really interested in how you can incorporate disorder or at different scales in your model, because in nature there are plenty of disorder, and it must have been selected through evolution because it somehow has interesting optical effects. And I was wondering, do you have any predictions that you make concerning disorder for Bragg mirrors or CLC? Does it stabilize the effect? Like, okay, this is roughness, but
yes.
For instance, at another scale,
yes.
Another.
So,
do you think it would? But because in biology, some like in morphos, they have shown that it stabilizes the signals, makes it visible from a larger viewing angles, which could be interesting for animals. But how can you incorporate that in your model? Disorder at other scales.
Yes. So there are two things I need to separate when we talk about irregularities. Here I mainly, yes, I talk about roughness, I wrote normal irregularities. Irregularities in normals. But as I told briefly at the end, you also have irregularities at the nanoscopic scale, where the thicknesses are not constant, where maybe you can also have variation in the composition of the material, varying the index. So the roughness, what is interesting with roughness is that it not only that does it influence the color, because it mixes the spectrum for different orientation, but it also change the appearance of change the scattering of light. And the more problematic part of nanoscopic irregularities is that we don't have yet a model to reproduce the scattering or to predict the scattering of light due to diffraction that those irregularities would generate. However, concerning the thickness itself, that varies, I think it would be pretty easy to have like same for microfacet, a stochastic distribution for each parameters. This is an idea I wanted to explore, but I didn't have time to do this. But yes, it was one of our idea at some point to have for each parameters some kind of distribution. And my guess would be that you would have actually kind of the same coloration, the same mixing of colors, because if you look at the spectrum, when you for example, when you vary the thickness ever so slightly, well, the band gaps, they shift a bit like when you move the angle ever so slightly. So my guess would be that the mixing of colors would kind of look like this, but with a more shiny appearance because you don't have actual roughness, actual geometric roughness. So that's my response. That for parameters, it should be very easy. For the scattering due to nanoscopic irregularities, it's another problem, and it's more an electromagnetic problem than just a spectral problem.
And if I understood well, in your Bragg mirrors, you take, you consider only a real a refraction index with a real plot, so no absorption. So I was wondering, in many animals, the layers with the highest refraction index is generally made of melanin or something like that. And melanin has an absorption effect. And when they did some measurements, Stavanger and colleagues, they found that it was not negligible. So do you think you could incorporate this complex part in your imaginary part in your model, or would it make it much slower to? Well, why did you make this assumption? Was it because you were afraid it might get too slow, or?
Not really. I mean, if you look this dispersion relation from the work of Potier and electromagnetics, actually you don't have to do any assumption on the imaginary part of the index. So all the accurate spectrum can easily be computed with melanin or a complex index. I did not implement complex indices in the renderer, mainly for simplicity. I will say it's mainly for simplicity. And I don't see any reason why our method wouldn't function with fluid system.
Good. Concerning your box approaches, we were wondering. So you make a box, okay, and then you say, okay, you have two different approximation. One is overestimating what occurs outside the band gaps, and the other underestimates it. But it's always waves, like it's always looking like that. Wouldn't it be simpler to just model a wave instead of a straight line?
I tried. I really tried to at least match the frequency, but I didn't succeed in finding exactly the
spacing.
Yes,
It's not periodic.
No, it's not periodic.
Ah, okay.
It looks a lot like the period is constant, but it's not. Neither when you look at it with wavelengths, nor when you look at it with the inverse of the wavelength. I tried so many times to find maybe it's no. Unfortunately, no.
I had some questions also about CLCs. It's really interesting, CLCs. I discovered the paper cited in the review of what in nature is made of CLCs.
Oh, yes.
And it's huge. Everything is CLC. From DNA to chitin, keratin, everything is bone and so on. And you said that when the liquid gets solid, it's like you have domains, special domains that tend to have different orientations. So you take a uniform distribution of this orientation. But then you later say that there are anchoring effects, like a predominant direction. And I would say that biologically, it's really like good to have a predominant thing. Well, sometimes it's uniform, but to me, it would sound logical to have some predominant directions, especially considering the mechanical effect. I don't know. I thought like that, but maybe not. No. So maybe I didn't understand this anchoring effect.
So yes, I will briefly.
Yeah. So
This is not from a biological point of view. Here I'm in fabrication process for this type of material, and in this fabrication process, notably the work of Bruno Federer-Petisik, what they had is a solution with these molecules in with some concentration. I'm not a chemist, but when the solution dries, when water evaporates, they reach a point where the liquid became a gel, and when the liquid became a gel, all the domains are stuck in place. All the rods get stuck in place. But before that, they had time to align with their neighbor and form this helical protein. And they do this independently in regions, and slowly this makes like cells where all the domains are aligned, but you have boundaries between those cells. When I say that there is a uniform distribution, it's before any alignment. We consider that all the potential domains are in all direction, and when they are stopped, when the liquid solidifies, you have a distribution of orientation that is uniform. And it's when the drying process continues, so we've reached a solid state, all the domains are stuck in place, but the drying continue, so they're squished, they are squished, and it's this compression that will alter the distribution. The distribution is not uniform anymore. So this is what happens, and this compression has two effects that has been shown in the work of Federer-Petisik and colleagues. Is that all the domains are like, if you have the sphere of orientation, well, the sphere gets flatter and all the directions are converged toward the normal. So you have, when each of them reflects, they reflect in the more and more same direction, so it feels more smooth. And also, well, the pitch, so the helix gets compressed in the direction of the surface, and you have you have this pitch tilt coupling equation, which grants really different appearance than when you don't have this process.
And I've seen in some beetles that I studied and in other articles that there can be a gradient of vertical gradient of pitches. So what is the effect of such a gradient on the appearance? And is it because, okay, I understand that in biology they have multiple roles from optics, mechanical roles, and it's better if you have different pitches. But what is the optical effect of such gradient?
There are a lot. The main effect is that you will accumulate. Thank you. You accumulate the band gaps if you reflect them.
So you kind of end up with white,
and you end up with not necessarily white, but with a broad reflector, and it's what gives some beetles are like a gold. There are like a gold color. It's like it's because the reflectance is a broad. It just a broad band gaps, ranging from yellow all the way up to red. It's done, yes, by having different pitches in the depth of the structure.
And is it something you can model in your bubble?
In first approximation, maybe we could, because just accumulating,
Okay.
to reflectance. But if you want to do this properly, it's a bit more complex, especially because we have to consider the polarization after each transmission. Because the polarization is rotated, and well, what gets through the first the first interface, the first pitch, it's polarized in the way that is not reflected by this pitch. So so you have to take into account now an incident light that is not unpolarized, and maybe it's simple, but we don't have developed a model for this.
Planar can do this?
Maybe. I think it would, yes.
Well, I think I'm done with the questions. I want again to congratulate you because you have really a talent for pedagogy, so you should exploit it in the future.
Okay, it has been more than 1 hour that you are answering some questions now. Tradition is that normally it's a time for me to let the advisor speak, but as president I can decide on this order. So I think I will ask only one or two small questions. Yeah, one was for the cyclical crystal. When you say that yeah, exactly this one, perfect. When simply you remove the shadow part of the BRDF, we discussed this in the previous question. Why not keeping it to allow some extra degree of freedom to try to do some other effect and so on? Does it change really nothing to have this degree of freedom?
It changes really not many things.
Okay.
The only reason I did this is because I wanted to present this particular structure, and you see that the surface, if you have an incoming light, the surface does not depend on the surface of one domain is not dependent on the orientation of this domain. Whereas in microfacet, the seen surface, or the projected surface of one microfacet is linked to the angle of the incidence, but also to the angle of the microfacet. And it's this decorrelation of the projected surface and the orientation of the domain that I wanted to have mathematically correct model. And well, because if you observe, it's not really just the G part, the geometric attenuation that we removed, but the bottom, the denominator is also different because of this projected area that does not change with the incident angle.
And I don't remember if it's in this model or in the previous one on the Bragg model. You say that part of you rely for the final model, still you have a pre-computed table for some part of the computation because you didn't find any basis function to represent it. even after, did you try to observe what are the shape and so on of this pre-computed typer? It was writing this, and even when we didn't find any.
It's complicated. I think it's for this term here. The main problem I had was to find the height of the purple box. The height of the purple box, I know it's linked to the anisotropy of the cholesterics. I know it's linked to the number of repetition. I know it's linked to the angle of incidence, but I didn't found any usable fit. I found some approximation, but they didn't work as well as just computing one big table but I still optimize this table because it only depends on those three parameters, knowing the angle, the number of repetition, and the anisotropy. So it's just a 3D, table with scalar in it. But yeah, I don't find it. I didn't study this 3D space to find a fit, for example. Nor have I found an analytical solution for this. But for the other, for the two other band gaps, I have.
Yeah, exactly. And last question, more open question. It was underlined in the report, and once again during the discussion now, the fact that we really have the ability to work in two domains, computer graphics and optics at the same time. For you, what was the most challenging part for working in these two domains? Is there any challenge, or it was simply natural to go from one domain to the other one? And more, during discussion, I see also a bit of the knowledge about the biology and so on during the discussion.
Well, I don't know. There are, I would say there are different challenges in each domain. In computer graphics, my main challenges was often the implementation of my lessons, especially when I had to implement our model into MRF, because it's coded in CUDA on GPU. Nightmare when you don't know what you're doing. And for the photonic point of view, it was also really hard because I had to read a lot of prior work. Notably, I read in all directions possible the books of Potier and the books of Belyakov to find ways to make them efficient. And the book of Belyakov is really hard to read. It's a nightmare. And even with the book, it was difficult to implement the method first in Python, even more in GPU. So I would say both domains had their challenges, but I like to work at the same time.
Thanks a lot. And so you decide which order to talk. Romain, Pascal.
Pascal. Je vais parler en français, j'ai prévenu Adolfo qui ne posera pas de questions, qu'on n'est pas censé poser de questions d'ailleurs. Et du coup, je suis très content parce que le jury a noté tes nombreuses contributions. Et puis, je pense qu'ils en ont quand même oublié deux. Je vais les mentionner. Donc, la première, c'est que tu as réussi à me faire stresser jusqu'à hier soir. Bien.
Mais ça, on pouvait pas. Il n'y a plus rien à avoir à dire.
Et la seconde, Gary, c'est que tu es l'illustration parfaite d'une réplique dans une série culte qui s'appelle MacGyver, je donne pour l'avoir eu, qui dit que la pression, c'est ce qui transforme le charbon en diamant. Toutes mes félicitations.
qu'est-ce que je vais dire ouais, tu t'en doutes bien, on s'est régalé, on a passé plein de bons moments à faire des brainstorms. Tu nous as appris autant qu'on s'est... Enfin, on s'est appris mutuellement, c'était super. Donc du coup, l'interaction entre photonique et graphique, c'était génial, ça. Donc comme toi, en effet, plein de fois, en fait, voilà, j'aimerais te rendre justice. Plein de fois, je t'ai dit que tu étais à l'arrache. Et en fait, je crois que j'ai compris ces derniers jours que c'est pas complètement vrai. Une chose au dernier moment, mais c'est pas à l'arrache, parce que je pense que la raison pour ça, c'est que quand tu as de l'enthousiasme sur quelque chose, si tu as quelque chose qui ne te convient pas, ben, tu vas à fond dedans, tu mets beaucoup de temps, et tu me passes beaucoup de temps jusqu'à ce que ce soit nickel, et c'est ça qui repousse le fait que tu puisses avoir les choses dans le temps. Je pense qu'on est assez d'accord sur ça, mais c'est aussi pour ça que tes présentations sont si claires et pédagogiques. Donc c'est un peu le revers de la médaille, donc c'est pas à l'arrache, c'est pas vraiment ça. Pas quel code du Gary. Et donc, ben, faut pas que tu perdes ça. Si tu pouvais être un peu moins stressant pour tes encadrants, mais tu n'as plus d'encadrants. Pour les gens qui sont à côté de toi. Mais au final, ça vaut quand même vachement le coup. Donc, merci.
Moi, j'étais en retard à le lire, hein, donc.
Moi, je suis pas l'habitude qu'on me l'envoie aussitôt.
Non,
écoutez,
c'est parfait. On a absorbé tout le stress. On a absorbé tout le stress. On a absorbé tout le stress.
Okay, so now we have to deliberate. We'll stay in this room. So je vais demander à tout le monde de sortir.
Oui.
Ah,
Sur l'intégrité scientifique, je crois que c'est
Là,
Après. Après. So, we have deliberated. Nous avons délibéré. I will say it in French. Nous avons délibéré et voici ce que le jury a décidé de dire. Donc, Gary Fourneau a présenté ses travaux à cheval entre deux domaines, la photonique et l'informatique graphique. La présentation ne tombe jamais dans l'écueil de se focaliser sur un seul aspect technique d'un des domaines. Les deux publics concernés, et même au-delà, puisqu'un domaine d'application est la biologie, ont trouvé le juste niveau de compréhension. Différents niveaux sont proposés pour que les experts et les non-experts puissent se retrouver. Le jury a particulièrement et unanimement apprécié la clarté du propos, de l'organisation de la présentation et des supports visuels. Cette approche est particulièrement visible dans l'introduction du contexte du projet ainsi que des travaux antérieurs. Cette introduction et ces travaux antérieurs ont été à la fois panoramiques et synthétiques. Cela prouve une grande qualité pédagogique. La présentation a permis de jeter un autre regard sur les travaux et de comprendre encore mieux leur ampleur et leur cohérence méthodologique. Lors des questions nombreuses, variées et multidisciplinaires, Gary a su encore faire preuve de cette pédagogie. Il a su s'adapter à son public en prenant le temps de choisir les mots. Il a su citer les justes publications pour soutenir son propos. Cela renforce le fait qu'il maîtrise son sujet et les domaines reliés, et même au-delà. Durant ces questions et ces réponses, des perspectives nombreuses ont été envisagées. Il a été noté par le jury que ces travaux participeront au transfert de connaissances entre les domaines. Il y a beaucoup à apprendre de ceci. Et pour tout cela, le jury voudrait féliciter Gary Fourneau et lui accorde le grade de docteur en informatique de l'Université de Bordeaux. Félicitations. Et il faut prêter serment.
En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes d'intégrité scientifique, je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Félicitations.
Bravo.
Bravo.
Merci beaucoup. Merci beaucoup.
Il y a Adolfo aussi.
Virtual handshake from here.
Là-bas.
Et moi, je le vois là-bas.
Tu fais quoi? Tu fais un discours ici?
Bon, bah, ça va. Je sais pas quoi dire. Non, bah, merci beaucoup à tous. Déjà, merci beaucoup au jury d'être venu et de m'avoir écouté pendant toute cette présentation. Merci beaucoup à tout le monde d'être venu et d'être resté même pendant les questions. Qu'est-ce que je peux bien dire? Ça fait 3 ans que j'ai commencé ce doctorat. C'était long. C'était pas toujours très simple, mais bon, on est arrivé au bout. Je vais remercier tout le monde. Hein. Je vais déjà remercier très sincèrement et très chaleureusement Pascal et Romain. Bah, merci beaucoup pour tout ce que vous avez fait pour moi hein, depuis 3 ans. Ça, c'est quand même, je sais pas, humainement et scientifiquement et dans tous les domaines possibles, c'était vraiment super génial. Je voudrais remercier énormément tous les amis à Manao, ici à l'INRIA, donc tous les doctorants, bien sûr Simon, Melvin, Pana, tous les non-doctorants, post-doctorants, stagiaires qui ont été là, qui sont encore là, qui reviennent même ensuite pour venir me voir. Tout le monde, vraiment, merci beaucoup d'avoir été une super équipe et je pense que je pouvais pas rêver mieux que de vous avoir avec moi pour travailler. C'était vraiment un super cadre. Merci à tous. Et merci aussi à tous mes amis qui sont venus là aujourd'hui. Et ça me fait vraiment plaisir que vous soyez déplacés juste pour voir des jolies images à l'écran. Et je voulais surtout finir par remercier Eliane. Donc, en 3 ans, il s'est passé pas mal de choses. Notamment, on s'est mariés pendant mon doctorat, il y a 6 mois. Et c'est la meilleure chose qui puisse m'être arrivée. Donc je voulais la remercier parce qu'elle m'a énormément soutenu pendant toute cette période. Et depuis une semaine, j'imagine que vous pouvez comprendre que ça a été un peu... Je voulais la remercier vraiment beaucoup. Voilà. Donc je vais m'arrêter avant de chialer encore plus que ça. Et on va aller pouvoir manger un petit peu. Parce qu'on a préparé quelques petits trucs pour le pot. Et je voudrais vous remercier encore une fois à tous et toutes d'avoir été présents aujourd'hui.
C'est vrai que l'usage est aussi de féliciter les conjoints de thèse. Donc, voilà, c'est ça. Bon, bravo aussi. On est passé par là.
Tu veux peut-être dire au revoir à Adolfo parce qu'après moi,
Merci beaucoup. Thank you very much, Adolfo, for having been present.
Oh, you are more than welcome. I had a lot of fun.
Thank you very much.
We'll drink for you.
Okay, see you, bye.
Bye bye.
C'est en présence.